I'm going to start off with defining a binomial distribution. It is a sequence of trials. So what I mean by that is we're going to do a bunch of things over and over and over again. And the binomial distribution is the collection of these trials. And we have four things that we're looking for here that we're going to list out. Um, Side note, if you've seen this before, you might have seen this as three things or five things because sometimes they get combined or split apart differently. It doesn't really matter. It's all the same pieces. So whether you remember it as three or four or five, as long as you have all the information, that's what really matters. So the first thing is that we have a fixed number of trials. What I mean by that is we say from the start how many we're going to have. This means I'm going to go out and I'm going to shoot 5 free throws, as opposed to I'm going to go shoot free throws until I make five. Because if I say I'm going to shoot free throws until I make five, how many trials does that take? How many shots do I have to take? Who knows? Maybe five, maybe 10, maybe 100, right? So we have to say how many free throws we're going to shoot, how many coins we're going to flip, these type of things. We're going to say how many trials we have. That is fixed. It does not go on until something happens. The second thing, each trial is independent of the others. And so that means when I do this sequence of events, that means, and we talked about the definition of independent, it means that what happens on one trial doesn't affect what happens on the next. Knowledge of what happened doesn't affect it, and or there's not like picking people out of a room and there's only so many people, and by picking a person out of that room now it affects my odds, right? That'd be that um, with replacement, without replacement idea that we had talked about before, right? So we have to make sure we have independent trials. Only one of two mutually exclusive outcomes can occur. And we think of those as success failure. Now, success failure is completely arbitrary. In my free throw example, it makes a lot of sense to say successes make, failures miss. But in a flipping a coin example, heads and tails, you define that success failure doesn't really matter, but we're going to constantly be thinking about it, even though it might be arbitrarily defined as success failure. The idea is only one of two things can occur, and those two things are mutually exclusive. Remember from chapter 3, mutually exclusive means that the two options cannot happen at the same time. So it's the idea that I can get heads or tails. I cannot flip a coin and get both heads and tails. If so, that would not be mutually exclusive, and that would be a problem. And our last characteristic of a binomial distribution is that the probability of success remains constant from trial to trial. That's related to the idea of independence. There are a couple of quirks where we can have an issue with one but not the other. The idea here is that whatever the probability is that I make the first free throw, whatever the probability is I flip the first coin and I get heads, that's going to be the same on the first trial as the last trial. It doesn't change throughout. And so this one can kind of go wonky. If you think through the sports examples and what happens if I do a handful of trials and I start getting a little better, I kind of find a little bit of a rhythm, find a groove, kind of figure out what I'm supposed to be doing. My probability of success might increase from the first trial to the 10th. Or you can go the other way. What if I do too many trials and I get fatigued? Now my probability of success is going to decrease from trial to trial because I'm getting tired and I'm maybe not performing as well. So that's kind of just a quick example of the way that can go awry. But it is related to the independence idea that we talked about there as well. And when we see these problems, we're going to have to identify. We'll do this later on this page of notes. Is an example binomial or is it not? And we're going to assess that by checking these four things. The answer to the question, is this binomial, is, well, are all four of these characteristics met? If all four are met, yes, it's binomial. If one of them is not met, then no, it's not binomial. If we have the random variable x, remember we defined in chapter 4a, we defined a random variable as taking words that would have come from trials, experiments, and putting them into numbers, right? And so the random variable is just I took my words of make, miss, heads, tails, whatever, boy, girl, whatever the setup was, and I turned that into numbers. If that random variable x is binomial, okay, and again, we talk about success fail. So if the random variable x is binomial and x represents specifically the number of successes, then we have a way that we can denote this. And this is the first time we've talked about an individual distribution. We'll do this again in chapter 6 with the normal distribution, but we'll say that x is distributed as binomial with two parameters, n and p, where n is the number of trials, as we said on the last slide were fixed, and P is the probability of success in a single trial, which remember we said stays constant across all the trials. So this right here, this little tilde, that means distributed as. So when I read this, I'm saying X is distributed as binomial with number of trials N and probability of success in a single trial P. That's how we read that statement out. And N and P are both going to be filled in with numbers in the context of the problem. So if I said I'm going to shoot 15 free throws, I'm going to let X represent how many I make, and I'm 40% likely to make any individual free throw, I would say that X, the number of free throws that I make, has a binomial distribution with N of 15 and P of 0.4. So we're going to plug in for N and P from the problem what those parameters are, what the number of trials is, and what the probability of success on one of those trials is. And then I have a note here. We talked about this a little bit earlier, this with replacement, without replacement. Sampling idea. Remember, we need independence among our trials. That's with replacement. That means we put the person back in the sample. That means the probability of success is going to be the same on the first trial as the last trial. Without replacement means I don't put the person in, and my odds change based off whatever happened on the first draw. And that's, again, the idea that, we're not saying we know what's going to happen on the first draw or the second draw. It's just saying that whatever I pick on the first draw, by removing that person, now my odds have changed. I'm not saying better or worse, it's just the odds are different now because I have a different set of people in the room that I'm picking from. And this note here just says if our sample size is less than 5% of the population, we don't actually have to care about that. And what I mean by that is if our sample is small relative to the pool of people that we're picking from. Okay, so the idea of this is simply if my population, and again, pause this and go back to chapter 1 if you're struggling on sample population. Remember, if my population is all Americans and I want to see how they will vote in an upcoming election. If I sample a really small subset of Americans, it doesn't actually matter if I do with replacement or without replacement. The idea there is that with replacement sampling says when I call a person to ask them who they're going to vote for, with replacement sampling means I put their phone number back in the pool and I have to call them again. Sorry, not have to call them. I have the opportunity to call them again. Without replacement means I don't, which that makes more sense. I wouldn't call the same person twice. And this is the idea that as long as I have less than 5% of all Americans in my sample, which, population of the country is 300 million, so 5%, is 15 million. As long as I sample less than 15 million people, probably not going to get that many people, then I don't have to care about it because I can treat my without replacement sampling as with replacement, so I can kind of check that box off even though it's a little bit fudged. So just the idea that as long as my sample size is relatively small with regards to how big the total population is, that characteristic can be kind of bent a little bit and it won't affect our math any. So some examples. Consider a standard deck of 52 playing cards and determine if the scenario described follows a binomial distribution. So the first one says if I pick 3 cards at random with replacement and I record their suit. And so if you want to pause and think through these examples, when I first read them, that'd be the time to do it. So you can kind of think through it now. The idea here is that I need to go through my checklist, those 4 characteristics, and say, are they all met? Again, if all of them are met, then good. If not, then we fail. And so in this case, if I were to record the suits of cards, then there are 4 different suits, which means I have 4 options. Now, those options are mutually exclusive, right? Mutually exclusive just means you can't have it at the same time. You can't pick a card and it be a heart and a spade. But the idea is that there are 4 different options that we record, and for a binomial trial, we have to have 2 options. And again, we think of them as success fail. So if we had changed this to recording if we have a red card or a black card, that would be a different story. But as it is, we have 4 possible options, which is not acceptable, and that makes this not a binomial trial. Next example, if I pick 3 cards at random without replacement, and I record whether they are face cards or not. Now, this is an area that a lot of people struggle with a couple of questions that pop up in homework and exams later on, where they start thinking through what the probability of success might be and saying, is that a problem? The idea that we need to remember is that the probability of success is constant. It doesn't matter what it is. It doesn't matter if the probability of success is 0.1, 0.5, 0.9. That doesn't matter. What matters is the probability of success the same? And in this case, if we were to think through the probability of drawing a face card in one trial, if I have all my 52 cards, there are 12 face cards. There's 3, a jack, queen, and a king for each suit. So there's 12 face cards. And I would say the probability of picking a face card on any given draw is 12 out of 52, which reduces to 3 out of 13. The fact that that's not 0.5 or 0.25 or some pretty number is completely irrelevant. The issue that we need to check for is, are the probabilities the same from trial to trial? Notice in this case, I have sampled without replacement. And so that's where this one's going to go awry, is by sampling without replacement. The probability that I draw a face card on the first draw is 3 out of 13, but because I have dependent trials, that probability doesn't stay the same from trial to trial. Okay, and so for this one, you can put either explanation. You can say the probability doesn't stay the same, or we have dependent trials. In this case, both of them are good reasons as to why this is not binomial. Next example, pick 3 cards at random with replacement and record whether they are face cards or not. This is the same thing we talked about in the previous one, except now by drawing with replacement, we put that card, whatever we got, whether it was a face card or not, back in the stack. And now I have a binomial trial. And every time we have a binomial trial, we need to stop and ask ourselves, what are the parameters to go with this? Okay, and this is going to be important for the binomial, it's going to be important for the normal, it's going to be important for sampling distributions later on. So this is a good habit to get into by saying, once I've identified something, follow that up with, okay, and what goes with it? Okay, good habit to get yourself into. So I've identified that we have a binomial. And again, just to confirm, let's check through our checklist, all 4 things. We have a fixed number of trials, right? That we're picking 3 trials. Each trial is independent because we're sampling with replacement. That's independent, right? Check back your chapter 3 notes to confirm that. We only have 2 options. You either get a face card or not, and you can't be both. You can't draw a card and it be a face card and not a face card. It either has a face or it doesn't. And the probability of success remains constant from trial to trial because of that with replacement. We put the card back in and we have the same chance every time. So it is binomial. We've gone through that checklist, and then we need to say what are the parameters to go with it. Remember, there's an n and a p. All right, that n is our sample size. The p is the probability of success in one trial. We've talked about both already. So you should be able to get there pretty quickly because we have already identified that we are drawing 3 cards. That means n is 3, and our probability of success we've already covered is 12 out of 52, which reduces to 3 out of 13. Make sure you catch there's a 52 in this problem. That doesn't matter with regards to n because n is our number of trials, right? There are 52 cards, but we're picking 3 of them. So we have a sample size of 3. The 52 comes into play in the fact that anytime I'm trying to find probability, I take the number of ways I can be successful divided by the number of total options, right? We did that in the chapter 4a and find it in that dice problem. And it's the same concept here. We say there are 12 different ways we can be successful out of 52 cards, gives me my probability of success. And in the last example, picking cards at random and recording whether they are a face card until we find 3 face cards. We kind of touched on this earlier. The issue here is that we do not have a fixed number of trials because I don't know how many times it's going to take in order for me to get 3 face cards. It might take 3 draws, it might take 6, it might take 12. Right? We don't really know, so that's not a binomial trial. It's a different kind of trial that is unique. It has a name, it has its own fun properties, but it's not one that we're going to discuss in this course. So now that we've identified binomials, which is a critical step 1, we have to be able to identify them. You might be asking yourself, why do I care, right? We've already covered how to work with means and expected values and probabilities of discrete variables. And if a binomial is a subset of a discrete variable, why does this matter? So what we're talking about here is, yes, everything we did in chapter 4a applies to all discrete variables. Binomial variables are a subset of that. They are discrete, but they also have these extra characteristics. And make sure you make that link, right? This is in the discrete chapter, so you should already be kind of thinking, yes, this is obviously discrete, but it's just a special kind of discrete variable, right? When you think about this binomial setup, if it's successes at a number of trials, there have to be gaps because you can't have half a success, right? So it makes it discrete right off the bat, and that we said the thing that differentiates discrete from continuous is that the gaps are not. You can't have 2.76589 whatever successes. So we have a discrete variable, so why do I care about these extra characteristics? Well, the answer comes on this next page of notes here when we say we have a binomial variable. These extra characteristics allow us to do what we did in the first part of chapter 4 a lot easier and a lot quicker. And it allows us to find the probability using a formula rather than have to be given a table. Remember, before we had to be given a table, or we had to have the right situation, like in that die example, to come up with that table on our own, right? But you aren't always going to have that given to you. So if we have a binomial, we can find those probabilities via a formula. And that's nice. Okay, so the extra characteristics allow us to find these probabilities. And that's what we're going to do here on this next slide, is we're going to say that the PMF of the binomial distribution is given via this formula. And there's a couple of things. First off, the n is taken off right there. So this should read 0, 1, dot, comma, n, as in x ranges from 0 to n. That should, I'm going to start off with that. Let's come back to all of this in a second. Let's start off with the PMF. Okay, the PMF, if you go back to the start of these notes, it's saying probability distribution, right? It's just saying, how do I assign a probability to my random variable, right? And so that's why we covered that in the first part of this chapter, some of that terminology, just to make sure you're comfortable with it. Again, remember, random variable just converts words to numbers, but then a probability distribution says I can assign a probability to each one of those numbers, right? So this is just saying, how do I do that? How do I get those probabilities? Okay, here's a formula. Again, we'll talk about the formula in a second, but we're saying those probabilities can come from this formula. And I want to start off with this: x ranges from 0 to n. Okay, and that should make sense to you. If you think about my coin flip example, shooting a free throw example, whatever it may be, right? If I'm going to shoot 10 free throws, I cannot have -1 successes, and I cannot have half a success, and I cannot have 11 successes. If I'm only shooting 10 free throws, I can't make 11, right? So I know all of the possible values x can be. So I could make a table if I wanted to, like we did in the first part of this chapter. I could make a table, and I could list out all the possible values. In that example, it would be from 0 to 10. And so in this case, again, we say x goes from 0 all the way up to n by whole numbers. This formula is how we calculate those probabilities. Remember, in a discrete probability distribution, f of x is probability. Those are synonymous ideas. Here's how we calculate that. This is combinatorics. If you've seen that, if you have not, that's okay. This reads n choose x. We can find it in Excel, a graphing calculator. Google can find you this answer as well. This is going to be a whole number. Then it's this times this piece times this piece. So you remember order of operations. This is p to the x. This is 1 minus p to the n minus x. We're just going to plug in our np's and x's from the context of the problem, and we can find probabilities. This is that n choose x. It also can be written like so. You might have seen it like that. You may see it like that on a graphing calculator. Also note that this 1 minus p is often denoted as q, and so we'll talk about that often. I'll throw out the idea of what q is. Q is just 1 minus p. Okay. Q is the probability of success. Remember, from our definitions, we said that P is the probability of success on any individual trial. So let's think that back through complements. The complement of a success is a failure. The probability of success is P. So the probability of the complement is 1 minus P, right? That should align with what we talked about in chapter 3. So we've done it in letters here, but the idea being, if I'm 40% likely to make a free throw, then I can do 1 minus that, which would be 0.6, and I could say that's Q, the probability that I miss a free throw, because that would be defined as the failure in that case. We also talk about mean and variance. The mean of a binomial is just n times p. So it's nice and simple. Instead of having to do all that complicated math where we did a bunch of summations and a bunch of multiplications, mean of a binomial, boom, n times p, nice and simple. The variance, same idea. The variance, n times p times q, or n times p times 1 minus p. And I don't have it written down, but of course, we should be very comfortable from what we talked about in chapter 2 about going back and forth between variance and standard deviation. If that's the formula for variance, if I need the formula for standard deviation, just slap a square root on it.